So it's my pleasure to introduce Hiraku Nakajima from IPMU. He will speak about Bow varieties and representations of affine algebras. So Nakajima-san.
Okay, thank you very much for introduction. So I'd like to thank organizers for invitation to giving me a chance to speak here. So I'll talk about Bow varieties and representation of affine algebras. Here is the plan. So I first give a definition of Bow varieties. So I have already explained Bow varieties at several occasions. So some people already know the definition, but I need to recall it. And then next I will explain the main result. This can be regarded as combination of two geometric constructions of affine algebra representation. One is based on quiver varieties, and that is all the result. And the second one is relatively new. So I'm recently trying to generalize geometric Satake for complex simple real algebra or complex reductive group with a case of affine group. And today's main result is that I introduce a certain variety which have both representations distributed. And then I conclude by so first I recall the quiver variety. So this is Hamiltonian reduction. Of products of some building block, which is I denote this way. So on the interval I put circle in the middle, and I do include the field non-negative integer 3 and 2. So these are the then this is just I take complex vector space T and T2 which you mentioned. Here are the vectors. Here, then this is subjective and action of 0, 3, 1 and 0, 3, 2. Only action and take various vector space, vector space and product and take a Hamilton reaction by product.
So is it just for me that the sound is not clear and there is some noise, or it's for everyone?
It's for everyone. Jan, you may want to mute your mic.
It's not my, it's not, I don't think it's mine, but let's try.
Yeah, I used in tablet mode, so maybe I try to. How about this? Still?
Yeah, it's better.
This is much better.
Okay.
Then for Bow varieties, we use two building blocks. Two types of. So one is the same, this one. And another is I denote very similar notation, but I just change the circle by cross. So this is another symplectic manifold. So this is not a vector space anymore. Complex simplex manifold with Hamiltonian GL V1 times GL V its action. In fact, I will add later after. First, I add also sister to here. So definition of this building block is as follows. I take again vector space V1, V2, and then I consider the space of linear maps like this. So this is A, and this is B1, and this is B2, and this is small a, small e. And I import the equation B2A minus A B1 plus small a, small b equal to 0. This is one equation, and there are two open conditions. So that it's a kind of stability condition. So there's no non-zero subspace, which is invariant under the B1 and filled by A and small e. So we assume there's no such subspace. And also there's similar condition. No subspace in V2, proper subspace, which is invariant. Okay. So this is a variety corresponding to this building block. So you don't need to understand the definition precisely. I mean, of course, if you want to really understand, study the properties of variety, you must be familiar with this definition. But at this moment, I used only basic properties of these varieties. So as I said, so I don't take any quotient. So I just impose those conditions. So you have the action of GLV1 times GLV2. And I don't explain what is the symplectic form. There is some explicit symplectic form on this. And this action V1, GLV2 are Hamiltonian. And also there is sister action acting on this sister, this C in the bottom. So this is Hamiltonian action.
And so the equation, it comes from some cubic potential, because this is a cycle.
So if you add, so in hidden, if you add arrow in this way, you can write down the potential, and then this comes from there. So I give some remarks. The first is, so this variety is introduced by Cherkis, but his original definition involves Nernst's equation. So this is certain ordinary differential equation, which is dimension reduction of instanton equation. So so this is some ODE, nonlinear ODE. So it is defined over the interval, and this is -1. And it is continuous at -1, but it has pole at the 0. So this is T. And in particular, so the rank, so this is defined, this is the matrix value. So something like T0 plus not TT. So alpha equal 1, 2, 3. And T alpha is matrix, and size are different from the left interval and the right interval. So here, size of matrix is equal to V1 in the right side, and here V2. And there's some matching condition at T equal 0, which is usually called the Nernst pose condition. So anyway, so this Bow variety is something appears in mathematical physics.
Why it's called Bow variety?
Hmm?
Why it's called Bow variety?
Bow varieties. It is due to Cherkis, so I'm not responsible. This is a cousin of quivers. Bow. You know what is bow?
Bow. Yeah, I know what is bow.
Yeah,
I do not see it. That's why I asked.
But so for quiver you have lots of arrows, and so usually I think the Cherkis usually denote interval by this kind of wavy lines, and okay. he understands this is a kind of bow. So that's what I understand. But name is just a name, no meaning. And the second remark. So that will if suppose I have dimension of V1 is greater than V2, then this Bow variety, this is isomorphic to GLV1 times slice to the nilpotent orbit corresponding to this Hooke-Young diagram. So this is V2, and this is V2 minus V1. So you have big block of size V2 and all other ones, right? And in fact, you not explain today, but you can show that arbitrary GLV times slice the arbitrary nilpotent orbit can be built from this building block. So in that sense, it will be built.
So is it V2 minus V1 or V1 minus V2?
V1 minus V2, I think.
Then probably V2 should be
this
bigger.
This is wrong, thanks. V1 is larger than V2. And if V2 is larger than V1, it's all the same, just to replace V and V2. And if V1 is equal to V2, then so you return back to. So in this case, you have this linear map A, which is between the same dimensional space, and then in this case, you can show that A is isomorphism. Then you can invert A, so then B2 is determined by from B1 and small a, small b. So then you can see that in this case, this variety is isomorphic to T star of GLV1 times C of V1 and its dual space. Okay. So I hope you see this. This is a symplectic manifold as I claimed. So this for this V1 equal V2 case, this is clear, I hope. And also, it is well known that if you take a slice and take the general linear group, then it is also symplectic. I mean, this is a symplectic. You can build this as a symplectic reduction of cotangent bundle of the group by some nilpotent subgroup, unipotent subgroup. So in that way, you can see the symplectic structure. Okay, so this is building block. So if you have any question? Okay. So then I use building these as a building block and construct complicated variety. So today I only consider variety of affine type A. So formally, I can consider introduce variety for associated with arbitrary diagram, but at this moment, its relation to representation theory is not clear, so I'm only concentrate in the case of affine type A. So I draw the so-called bow diagram. So there is a big circle, and I put small circles and small cross on those diagram in arbitrary manner. And for each segment, which is separated by either circle or cross, I assign integers, non-negative integers like this, P0, P1, P2, and so on. Then, so according to so I can divide these into pieces like this, and then you see the building block, which I just explained, and take corresponding variety. So from border, I consider product of and this one. And then take so Hamiltonian reduction. By the product of G. Okay. So this is the definition of variety. And as in the case of quiver varieties, when I take Hamiltonian reduction, you can perturb the equation, momentum application. Or you can consider the GIT constant, can consider. So this is as usual for the quiver varieties. So there's one technical remark on this. So a priori, you can maybe you can consider perturbation of the moment of equation or GIT quotient for arbitrary group, but in fact, you can see that it somehow depends only on the difference of two groups, adjacent groups, and so this is so this is possible for this the symplectic vector space which appears in the definition quiver vertex, but not. So you can formally define the geometric quotient or perturbation moment for this new building, but that it doesn't. That just gives us trivial deformation and the trivial geometric quotient. So actually, the number of parameters for geometric quotient is number of parameters for deformation work. Or geometric quotient is equal to number of circles. Okay. Then I introduce conditions. So Bow diagram. I say Bow diagram is balanced. So for any circle, there are two integers assigned. For any circles, V1 is equal to V2. So this is balanced condition. And similarly, I change the circles and cross. So this is balanced and cobalanced condition. Then theorem, which is due to Cherkis, is a following. So if you consider the cobalanced Bow variety, so this is isomorphic to quiver. Affine type A. So this is not so difficult to prove. So
this condition, this condition, it's a sort of a removal condition, so you can remove one type.
Yeah, I will explain now. So,
Okay.
so we have this kind of situation. So balance that the dimensions for neighboring to close are the same. So I have V0, V0. So this is all the same dimensions. But if you cross the circle, the dimension can be different. So we have V1, V1. This is Vn minus 1. And so on. But recall, I mentioned that if so for new building block, if the dimensions are the same, so this part is T star of GL V0 cross C of V0 cross C of V0 star. But when you consider the Hamilton reduction of the cotangent bundle of the group, this is trivial, how to say. So you take the product with cotangent bundle of the group and take the Hamilton reduction by the group itself, then it's the same as the original variety, right? So the only this remains, this part remains. So from this, you see that vector spaces, and this is just a homomorphism from between C one-dimensional space and C of V0. So if you have number of, so W0, I did not define W0, the number of cross between two circles. I have several crosses. Then I can just replace V0 and W0. W0 is just a vector space of dimension W0. And then I have V1, and similarly I have W1. Okay, so in this way, you just see the original definition of quiver practice. So then, so this is a case of co-balanced one. So I just, but I consider the balanced case. So this is what I proved with Takayama several years ago. If instead I assume balanced condition, balanced probability. So this is isomorphic to Coulomb branch. Of quiver gauge theory. Of affine type A. So this Coulomb branch was defined earlier by my joint work with Braverman and Finkelberg.
So these discrete parameters, they appear.
So there are various variants of Coulomb branch. So the most fundamental one is the spectrum of commutative ring. This is the affine object variety, but you can, so once you have the so-called flavor symmetry, so the quiver which I use to define Coulomb branch is the same as the quiver variety for cobalanced, but I just replace the cross and the circles. But still, because of the symmetry of the graph, you can still have the quiver representation by the same rule if I just replace cross and circles. Then you have flavor symmetry. So general linear groups of W zeros are called flavor symmetry groups. And once you have such structures, this gives us deformation and GIT parameter. Yeah, maybe I just should record the general expectation between Higgs and Coulomb branches. So quiver variety is Higgs branch. In this particular case, but it's much more general. So in this case, starting from symplectic representation of a group, you can assign two symplectic varieties. One is called Higgs branch and the other is called Coulomb branches. And for quiver gauge theory, this Higgs branch is just quiver varieties. And in this construction, so the flavor symmetry, So flavor symmetry is additional group acting on the vector space, which is different from the original gauge group. So original gauge group is general product of general linear groups of V's in this case, and the W is just additional symmetry. But once you have flavor symmetry, so on the Higgs branch, you have the Hamiltonian action. Because I only take the quotient by the gauge group, general product of general unions of VI's, and so the flavor symmetry group acts on the quotient space. So this is Hamiltonian group action. So on the other hand, on the Coulomb branch, so this appears as deformation or GIT parameters. So people often say this is mass parameter. And in this Higgs and Coulomb branches, mass parameter and GIT parameter or Kähler parameter appears in different. And if there's something opposite, so you can consider the GIT parameter for the Higgs branch that plays a role for mass parameter for Coulomb.
So you're saying that this Bow variety is somehow symplectically dual to quiver varieties?
Yeah. Yes. No, I don't say this is. So Bow varieties are assigned for this Bow diagram. So this is 3D mirror. So I just replace circles and cross. So in general, Bow variety is not gauge theory. Bow variety is not either Higgs or Coulomb branch of Bow variety. So this is associated with some kind of mysterious four-dimensional and three-dimensional n equal 4 supersymmetric Compton field theory. But you can assign two theories and for Bow diagrams, and so you can consider two varieties. First, I define Bow variety for this diagram, and the second for this Bow diagram, just exchanging circles and cross. So is it clear?
No. I mean, it's not clear for me. It's not clear why they're exchanged in this way. So
yeah, so it's even not clear to me. I mean, of course, the definition. If you go back to the definition, so this one is using vector space, symplectic vector space like this, and the other is this bit more complicated, and this is slowly slide product of general and slice. And why they are dual to each other, it's not so clear to me, but by experience, we can see many phenomena which, how to say, for which you can see the duality. But so this, as I said, for if you assume balanced conditions, then corresponding Bow variety is the Coulomb branch. And if you apply this exchange of circles and cross, then another diagram satisfies co-balanced condition. And then you have, that is corresponding to quiver variety, which is Higgs branch. So this is a generalization of the exchange of Higgs and Coulomb branches. Right. So this as far as I know, this example, this duality includes all the known, basically all the known examples of dual pairs, symplectic dual pairs.
Yeah, it's interesting. Another
So
interesting.
I think this is most generous. So Coulomb branches have more general definition, but usually Coulomb branch becomes singular. And if you really want to have Coulomb branch which has symplectic resolution, I think this is the most big supply of examples. And so far, I think all the examples known are based on this, the special case of this. Okay. Now, let me explain the main result. So from now, I only consider the case deformation parameter is equal to 0. And I consider zeta, which is generic stability condition. In fact, the stability condition which I always use for quiver varieties. So I denote the corresponding Bow variety by M zeta. And also I use zero stability condition. Zero stability.
So for generic, it's smooth, yeah.
This is smooth. Maybe I didn't say that. This is smooth. Zero stability. This is so M0. So this is categorical quotient. And you have always the morphism like this. And in many cases, so this is symplectic resolution, but not in general. So for example, for quiver varieties, I hope you know that there is some dominance condition to guarantee that this is symplectic resolution. But for Coulomb branch, it is known that always this is. So in that sense, Coulomb branch is much nicer than quiver varieties for this problem. So anyway, we have this, we consider pairs of Bow varieties M zeta and M0. And as I remarked, I have the Hamiltonian sister action for each cross. I have sister. So I have in total sister to the power n. So n is from now on, this is number of crosses. And I denote L, this is number of circles in both. So I have Hamiltonian sister n action on M zeta and M0. And this morphism is equivariant. Okay. And for Bow diagram, not for Bow diagram, we just only consider the circles appears in upper hemisphere and the cross appears in lower hemisphere. Right, like this. So in fact, this is not any loss of generality. In fact, by the so-called Annan-Witten transition. So this, once you have the circles and cross like this, then this is isomorphic V1, V2, V3. This is isomorphic to just this one, V1 and V3. And this V2 is changed. V2 prime is V1 plus V3 plus 1 minus V2. So this, you take two building blocks and take the product, and you just exchange the order of cross and circle. Then the Hamiltonian reduction are isomorphic. So this is called, this is originally found by Annan and Witten. I proved as an isomorphism of symplectic manifolds, and we call it Annan-Witten transition. So from this rule, so you can change the order of circles and cross. So you can, because of this, you can move all the circles to upwards and all the times cross to lower hemicycle. So it's no solution. And we consider arbitrary dimensions. Right? So we have infinitely many Bow varieties assigned for this Bow diagram, but dimension vectors are arbitrary. Okay. Then I will consider some homology group of Bow varieties and try to relate it to representation. Okay.
They are non-compact. Yeah.
They are non-compact. Yes, they are non-compact. They are case project. Maybe I didn't say so. M0 is an affine variety. So this building block, product of general linear group and slice is affine variety. So maybe I didn't say. So it's not clear from the original definition because I import some open condition, but I state that this is in fact isomorphic to product of general linear group and slice or this cotangent to the group. Both are affine variety. So M0 is a categorical quotient of affine variety. And M zeta is GIP quotient. So M0 is affine variety, and M zeta is K-sign projective variety, which is proper over projective over affine. So this. Yes. So let me make a little bit more precise. So this is not the ordinary homology of M zeta. That doesn't behave well. And if you are familiar with geometric circle, then you see why the following construction is natural. So I take chi. So this is dominant co-character. Well, dominant is, maybe I don't explain properly, but some condition, genericity condition. Then I consider the attracting set. So this is so you can define similarly M0, the attracting set for M0. And you have project movement. This is inverse image of this attracting set for M0. Then theorem, so which is joint work with Muthiah. In progress. So, in fact, you can also show that this is Lagrangian EMZ. So you have a Hamiltonian group action, and maybe I should mention that this has so if you consider the fixed point, this torus. So since I take generic co-character, so this is the same as fixed point with respect to C, with respect to chi of C star. So this is isolated. You can show that this is isolated.
Is it finite? Oh, okay.
Yeah, finite. Possibly empty. So if this is empty, so if limit exists, then the limit must be fixed point. So if there's no fixed point at all, then this attracting set is empty. So when I say this is Lagrangian EM zeta, so I allow possibly empty set. And the homology group of empty set is zero-dimensional vectors. That is my convention. So anyway, you consider this homology group of this attracting set. And take all dimensions, like sum over all dimensions.
All dimensions, what do you mean? All.
So I have diagram. I only fix the shape of diagram, but we have V0 and V1 and
Okay.
And so on. I consider all the dimensions, VIs. As in the case of the usual relation between the representations.
Yes, so it will be kind of a highest weight representation rather than finite dimensional. Because
this
it's
is a representation of affine algebras.
Yeah, but is it what highest weight or what?
Yeah, I will explain.
Okay.
Representation of commuting SLN affine and SLL affine. N is number of cross and L is number of circles. And the statement is, all the statement is somehow it has a symmetry. So if you change the cross and circles, so this SLN and SLL are exchanged. And in fact, even more.
So it's what is it? No, what kind of duality is it?
Yeah, I will explain. It is isomorphic to Fock space. So this is defined as semi-infinite product of slight variant of the usual Hawk space. So I first take n-dimensional vector space and l-dimensional vector space, and I take tensor product, and I take the usual construction for Laurent polynomial. This is it. Then, so you see that Cn, because I mean, if you just constantly forget the Cl, then this is a copies of L, direct sum of L copies of Cn tensor with this Laurent polynomials. Then you have the action of the affine SLN by the usual construction. And if you instead, if you consider CL times Laurent polynomial, then you have the action by SLL. So this is the Fock space which both you have the action of both SLN and SLL simultaneous. Okay. So now, so this is the main result. So any questions?
Probably you explain more what that mean. If you interchange you in this duality and NL,
how's the center acting on this for each one of them?
So level is maybe. Level for SL n hat is equal to L, and the level for SL L hat is equal to N.
Oh, so it's kind
okay,
of
so this is a level duality.
Yeah.
So in summary, so this homology group of this Bow variety realize the level rank DI. So remarks. The first one is, so SL Hattel representation. So this is a modification of the quiver variety case. Quiver variety construction. So namely, I introduced some correspondence in the product and define the operator corresponding to Shiga generators and check that it satisfies the defining relation affine. So on the other hand, affine SNL representation. So this is the modification of the geometric Satake. For affine real algebras. Which I'm recently studying. So originally this is proposed by Brevan together with Brevan interval. So this is based on the as in the case of the usual geometric Satake as formulated by Markowitz Belonen. So we consider the hyperbolic restriction of intersection cohomology of singular line. So, but maybe I didn't say that this homomorphism, I denote this homomorphism pi. Maybe this is second. So I have projective morphism from M0, zeta to M0. So this is semi-small morphism with respect to target. So in the definition of semi-smallness, you usually assume, implicitly assume this morphism is surjective, but this is not surjective in general. So if you just replace the target space by the image, then this is. So from this, so if you consider the constant sheaf on M zeta and take pushword, then it decomposes into IC sheaves of various stratum. And you can also show that there's no local system appears in this decomposition. And no, tensor with H top of fibers of fiber. And this is stratum. So SL L hat acts on the top degree homology of fibers, and SL N hat acts on the maybe I need to go to next page. So this is similar to Markovitz. Willonen's formulation. For geometric Satake. Right. So the two constructions looks very different, and I don't see any direct relation between them. But if I really try to compute this representation explicitly, then I somehow after the computation I see that two constructions are exchanged if I extend the circles and cross. So in order to perform this explicit computation, I briefly mention what kind of description I use. So for this kind of game, it is important to describe. How many moments I have? Almost to finish description. So in fact, this H top of attracting set has a basis parameterized by fixed point. So maybe this is most elegantly explained by the notion of stable envelope developed by Moik and Punk. But anyway, so roughly, you just consider take a fixed point and consider the attracting points which floats to the given fixed point. Then it forms some sub-variety of the top dimensions. And fundamental class of this is a basis. And in fact, it turns out that this is not a good basis. And stable envelope is a modification and having upper triangular property to this basis, which I naively explain. So anyway, so this it is important to describe fixed points, and this is given by Maya diagram. So I have this kind of picture. So I have n columns and L rows, and it continues to left and right. So I say that this representation is semi-unit product of CL tensor CL times C to the Laurent polynomials. And this, of course, this each block corresponds to CL tensor CL, and so it is goes to infinity, and so this direction corresponds to T. It goes to infinity to right and infinity to left, and that's going to the powers of T. And so this element is something like V. Basis is given by Vi tensors W J tensor T N. So this, no. First I take a basis of this one. And the semi-infinite denoted by V I J N. So semi-infinite is product exterior powers is V I 1 J 1 N 1 which V I 2 J 2 N 2 and so on. So this is a basis of F if I run all i's and n's. So corresponding to appearing the vectors appearing in this, I just put I color the corresponding box by black. Then I get these kind of diagram. And semi-infinite means that so far east, far west, all the boxes is in black, and for far east, this is the white. So this is the condition. So Fock space, that means Fock space has this basis, and that is realized by this fixed, which I just said, as I said, this corresponds to basis given by fixed points. And in this way, you can show that this direct sum of top degree homology group of this attracting set is isomorphic to Fock space. And you can also show that the action of the affine layers explicitly, and this is just changing the black and white boxes as in the usual cases. And from this description, and also under this exchange of circles and cross corresponding to the exchange of so transpose of my diagram. So I have this L and N like this. Then I take transpose for each blocks. So this is basically just given by exchanging Cn and Cl. So that corresponds to transpose for each box. Okay, then from this computation, you can check that if I impose this exchange, the action, two action is exchanged. And so as a geometric application, so this as a consequence, so m zeta c star to the n, number of fixed points is equal to number of fixed point m zeta, but you just exchange circles and cross and torus fixed point. So torus, dimension of torus is different. So one is n and one is l dimension. So this statement is not obvious at all, but because they are both parameterized by Maya diagrams, and Maya diagrams have natural bijection just given by transpose of diagrams, generalized diagrams, transpose of Maya diagrams. So because of this, you have this equality. So this is one of the first tests for 3D mirror symmetric pair. So you consider torus Hamiltonian torus action, and the number of fixed points must be equal if the varieties are pairs. Okay, I think I almost, yeah, I'm sorry, I already.
No, you can go over time. I mean, your day is just started here.
Well, that is true. Well, but I think I more or less said everything, all what I want to say. I stop now and try open the session for questions.
Okay, so questions. Are there any questions? I don't know whether people hear me. I do have some question. Probably you have this quantization procedure of Bow varieties, even if it's not a Coulomb branch or something.
Yeah, so because that is some research project which I proposed to several students, but nobody are interested in so far.
Okay,
so
maybe some of our students.
yeah, very welcome. So this is, I defined Bow variety based on two building blocks and take Hamiltonian reduction. And once you have quantization of blocks, then Hamiltonian reduction has a quantization called quantum Hamiltonian reduction. The definition is basically the same. So, but if you look at the building block, then one is just a symplectic vector space. So if you just consider differential operators acting on the one piece, Lagrangian subspace, then it is a quantization. And also, if you look at this new building block, then in fact, even starting from this description by matrices, in fact, already Finkelberg and Rubinnikov considered quantization. This is one approach, but another approach is, as I explained, so if depending on the inequality between dimensions, it is either product of general group and slice, or cotangent product of cotangent bundle. And this has quantization, clearly has quantization. And this has quantization by W, finite double algebra. So you can just study the starting from these building blocks, you take the product and take quantum Hamilton reaction. So you have the quantization of both varieties. And for the Coulomb branch, if the variety is a Coulomb branch, it has its own quantization that is called quantized Coulomb branch and defined very almost just I mean, if you know the definition of Coulomb branch, it is automatic to quantize it. And so I proposed to students to show that this quantized Coulomb branch is isomorphic to this quantum Hamilton reduction, but nobody is interested. So this is one open question. And the second, you should study the representation theory of this quantization of both varieties, and the expectation is similar to this statement, which I just explained. So corresponding to the attracting set, this corresponds to considering certain category O. So you must define category O appropriately.
Geometrically.
So then you see that you should define some functors on category O for this quantum both varieties, and that realize the categorification of this result, which I just explained. And you can realize level rank duality in a categorical sense. So that is natural to expect, I guess. Does it answer to your question?
Yes, to probably to the extent to which it can be answered. Yeah, you explained. Yeah.
But I'm not, the one caveat is that, so once you take the product of some building block is just a finite double algebra, so this is easy. But once you take product and take a Hamiltonian reduction, I'm not sure this is easy to study. So I spent many years to study quiver varieties, and I get used to study its geometric properties. But for quantum Hamiltonian reduction, I'm not get used to. So I don't know if this is easy problem or not.
Okay, thank you. More questions?
So you just say you have the finite W algebra structure, but can you get to the affine W algebra or even W vertex algebra from this?
This is, I mean, this is just a definition. So for each building block, I assign Hamiltonian vector space, symplectic vector space or slices. Then for quantization, I just replace this by differential operators on vector space or finite double algebra. But I can further replace them by corresponding vertex operator algebras. So one is just free fields. So this is a vector space we just replace by free fields. And for the second one, you just replace finite double algebra by usual double algebra. And then take product and take quantum Hamiltonian, quantum Greenfeld-Sokolov reduction. So in that sense, you can define the vertex operator algebra corresponding to both diagram. That is possible. But I don't know. So nobody studied. And
well, we did for the level rank duality in the vertex algebra case, and in this construction, the representation looks to be the basic representation for SL L times N. And both copies of SLN and SLL are kind of embedding inside and mutually commuting. This is still quite mysterious from vertex operator algebra viewpoint.
I'm not sure this.
from the semi-infinite wedge product construction.
So I think that, so if I consider the vertex operator algebra, then I must consider the, as I said, where it is. I must consider the corresponding category of vertex operator algebras, and that should have this symmetry. But I mean, this double algebra is a reduction of affine algebra, but this N and L are nothing to do with this rank or levels of the affine vertex algebra.
But if you look at the semi-infinite wedge space, which is a C, I mean, as a vector space that's n times L dimensional.
Yeah, this semi-infinite wedge space is a representation of certain vertex operator algebra,
but on the geometry side, I'm not sure how.
From the one which assigned for both diagram. So the relation is not clear to me. So I can just formally, in the level of definition, I can just formally replace the definition of Bow variety as definition of some definition of vertex operator algebra, and maybe its category of representation has interesting structure, but this is another story, and I don't a priori I don't see any such structure if I stay in the level of definition.
And these Bow varieties, they probably describe some geometric objects which quiver varieties do not capture, some moduli spaces.
Yes. This is a modular space of instantons on the so-called multi-tabulato space.
With what condition at infinity?
There's some different condition at infinity. So Bow variety maybe where I should. Yeah. So Cherkis prove that Bow variety is modular space. So this is a kind of ADHM type description. So long time ago, Coulomb and I proved that quiver variety is modular space for instanton on A spaces. So both are C2 divided by cyclic group. But have a different Tabunat and area have different hyperkilometry. So in particular, if you consider the corresponding instantons on the multi-tabunat and area spaces, they have different boundary behavior. That's the reason why Bow varieties are more general than the quiver. And I don't know have a physical explanation, but it seems for various dualities, tabunat space appears more naturally than area spaces. So that's the reason why probably we can see this level rank duality for Bow varieties, but we cannot see the level rank duality in quiver varieties. That's my understanding why we have this result, main result today for Bow varieties.
And so these actions, they kind of generalize all the results about the action on the cohomology of usual moduli spaces of instantons. Yeah? Okay. Okay. More questions?
Let me ask one more question. Looks even though you are looking at the type A cyclic quiver for the ball variety, that can be defined for any quiver once you mark some of the arrows with a circle, some of the arrows with a cross. And what happens if you have between two vertices and you have double arrows and with one circle, one cross? Will that make any sense in the construction of ball variety?
I'm not sure I understand what I mean.
Well,
maybe
so far
you should draw the diagram. I mean, I can consider.
Okay. So I regard the circle is just the markings on the arrows of the quiver. Yeah.
So I can consider more general diagram like this, but I think for type D, I think I understand what corresponds. I mean, this is first of all, I'm interested in this such a generalization should be Coulomb branch of some gauge theory. And otherwise, maybe it's just a definition. It doesn't worthwhile to study such a spaces. But at least for type D, it seems this is a Coulomb branch of some particular gauge theory.
Okay.
So I am convinced that this is a reasonable space to consider. But even if I consider more general case, then I'm not sure this is something interesting space to consider.
I see. So especially between two vertices, if you have multiple edges, that probably won't make much sense from a physical viewpoint.
Yeah, physicists. I mean, so this diagram is realized by brains, and physicists have some restriction on the arrangement of the brains, and they usually consider only affine type A, and they impose some condition in some cases, but I think I'm not sure. So they study the type D cases. Yeah, one of the variant for which my students study is why I impose the symmetry on these ball diagrams, and if I consider the fixed point, then it seems this is a reasonable space to consider. And one of my students study these fixed points.
But I was curious about the level rank duality in other types other than just type A's.
Yeah, that is
in representation viewpoint.
But the level rank duality, I mean, of course, you have level rank duality for other groups, but as far as I understand, it is most elegant for type A, and for type other types, it becomes a little bit more complicated and it's less clear. So
well, on the vertex algebra part, there was some work done for the type B. So I'm not sure whether the formulation this way will be able to extend.
Yeah, but the point is that there is kind of a different type of duality, which is this mirror symmetry, or more generally this bow quiver dualities between different things. And this level rank is just a special case.
That's right.
If I understand correctly.
Yeah. So for this kind of duality, there are various examples, but I don't have any conceptual understanding to produce examples. So I study. I don't have any theoretical clear picture to produce dualities in general.
And for example, some of those from the affine or the finite type have a quiver with the automorphisms. That whether it's a twisted version or the type B version, that gives. So whether that will work in this way, and what is exactly the right level rank duality other than type A, still not quite clear.
Yeah, one interesting question on quiver varieties is how to realize non-symmetric Katsumudiri algebra in quiver varieties. And I have been studied many years, but I didn't have good understanding until recently. But when I found the definition of Coulomb branches, I found that for Coulomb branches, it's rather easy to generalize for symmetrizable case, non-symmetric cases. And that gives some hint how we should consider this problem for quiver varieties. That is my current hope. Certainly, I mean, people study the duality for non-symmetric case, so that kind of study must be done.
Okay, well, thank you.
Okay, are there any further questions? Well, if not, let's thank Hiraku Nakajima for very beautiful talk, very inspiring. Thank you very much.
Thank you for attention.